last talk, and thank you to the organizer for this great show. I've had a great time so far. Let's see how it continues. But it was also nice that, I don't know if you attended Nils's talk, but his title was actually "Attention is not all you need." And so that this is a pun on the same paper, I guess, but also an answer to his talk, I guess, because language modeling is all you need. So that's cool. So I'm here from Seal Software. We do a lot of NLP stuff, and I will be talking about how we use and what language models are today. So when I got into this NLP business like 2-3 years ago, I was immediately drawn to these language models, which are sort of the pinnacle of deep learning in my mind, at least. And they sort of delivers on the promise of deep learning that you can sort of use all your unlabeled data to provide some business value. So I'll be talking a bit about that today. And it's also nice, in the last year, the theory of language models have really sort of exploded, which sort of started last summer, I guess, and sort of just continually, increasingly became more and more about this. And I guess the pinnacle was a couple of months ago when OpenAI released their, or did not release their big language model because it was sort of too dangerous for the public to handle. I don't know if you heard about that, but that sort of spawned a lot of attention, and all of a sudden I got a lot of questions about what are these language models, and hopefully I can tell a little bit about that today. All right. So let's just start with what a language model actually is, in my mind. So it's a probabilistic model that, given some context, it tries to predict a word. So for instance, if you look at a sequence of words, maybe you try to predict the following word here, like in a sentence. So here's an example of a sentence. So the woman heard that computers, and here we're trying to guess what this word could be. And since you are humans and you know a lot about language, you sort of have a lot of probable words that could pop up here, right? But for a computer, this is just symbols. It doesn't know anything yet. So the language model here tries to calculate the probability of this word, given this context here. The woman heard that computers. So the way this works is that we sort of just list all the words that we know in the English language, and we sort of assign probabilities to each one of them. Or that's what the language model does, at least. I don't know if you do that on a daily basis. What do you do, actually? Okay. So once calculated, it sort of scores these as probable continuations of this sentence. So now could probably fit there. The woman heard that computers now do this. That's probably okay. The woman heard that computers soccer, probably not so probable, right? And before we move on, I just want to touch briefly on what they can be used for. So one main usage that you all have been experiencing is auto-completion on your phone, right? There is actually a sort of a language model in there that tries to predict what your next word is going to be. It's used in speech recognition software to disambiguate. When it doesn't really hear what you're saying, it can sort of infer from the context, okay, it's probably this, it's not that. Auto responses to emails, and question answering, and text classification, and this is the big one we're doing at Seal, mostly at least, where we try to classify text in terms of, is this a contract or is this something else? And it's also widely used in language translation, translating between languages, and much more. So I thought I'd just dive in a bit into the architectures that are actually used here. So we've seen quite a lot of these during this day, but I still think it's very fun to sort of dive into what's really going on in here. So basically here, this is the recurrent neural network architecture that some of you might be familiar with. And the game you play when you do like NLP deep learning is that you represent words as vectors here. So xt would be the input word, represented by this vector. And U, V, and W here are matrices. So actually I think I drew, yeah, so they are matrices. And these columns here they represent vectors. And the input here, as I said, a word gets represented as a vector. You plug that into this RNN function, which is basically just some matrix multiplication and addition, and you follow that by some nonlinear function, sigma. And then YT will be this vector of probabilities over all your words in the English language, for instance. So it's the softmax of another nonlinearity, and it's just probabilities of the words. So you have this recurrent structure indicated by this loop here, but I will actually roll this out because I think it's probably a bit easier to understand. So this is the same picture, but sort of the loop is unlooped. And here we have a sentence: robots learn how to speak English. That's of course what we're trying to accomplish here. And we input the words down here. So x0 is robots, x1 is learned, and so forth. And we feed those in, using this vector representation, into this RNN units that we saw previously. And what happens then is that each RNN computes a state, which is sort of passes on to the next guy. So this is H0, and it uses X1 and H0 to go forward to produce the next states for the new RNN. And at this point, you take X2, plug it in there, you use the state from the previous RNN, and you go forward in this fashion. So once you go here, so robots learn how to speak, and then you want to sort of predict at what it's going to be. Then you look at, okay, so what is Y for? It's a probability over words, and in this case, we want to bias this, train it to learn that it should be English. So probably you have noticed that what I have upstairs as the output to this is just the same sentence, just shifted one to the right? So we want robots to predict learn to predict how to predict to, and so forth. And so when you do this and you go through here, you get out this vector here, which sort of represents the whole current state of everything that is seen before, right? And one of the problems here is that it's pretty hard to actually pass through information through all these bottlenecks. And we know that sort of information tends to disappear, especially if you have even longer text sentences. So of course this is a very short sentence, but we use this for long sentences, and then that information has a problem to propagate forward or backwards, depending on how you think. And so I indicated this by memories fading here, so it's hard, it sort of gets shady the longer you go. So one can ask, is there something we can do for this to just take a sneak peek at the states here, at all the previous states, instead of just relying on this bottleneck representation of RNN? And you can, and the answer to that is attention, which received a lot of attention a couple of years ago. And it works like this. So this is the same picture. I just removed the outputs of the other ones there, the Y0, and just focus on Y3. And so what happens here is that we take the words. So robots learn how to. From that we get this H3 representation, right? And this encodes the entire sequence state from before. And H3, we now allow H3 to actually ask, like H2, H1, H0, hey, do you have any information that is needed for me, or can make it easier for me to predict what the output Y3 should actually be? And then you have to ask yourself, well, okay, so how do vectors speak? And, well, the way they do it is by, in this case, the dot product. So you just take your vector H3, and you ask H2 by computing this dot product with itself. And if this is large, that's H2 telling H3, yeah, yes, I think I have something for you. And it can do this with all the previous states. And if this is a large number, for instance, if H0 dot product H3 is large, then it's a sort of affirmative. I have something for you. If it's very small, I don't have anything for you, so don't look at me. And from this, you sort of build up the attention vector, as it's called, A3, denoted here. And it's just a weighted sum of all the previous state vectors you have from here, weighted by how much information they have to give you, in some sense. You have this exponential here, and you also have some normalizing factor, but that's not so important. So just to iterate, like at time t, you do this. You let the hidden states of the RNN sort of ask all the previous hidden state, do you have something for me? And you compute this attention vector at time t, which is sort of a much more lightweight representation of information from the past. And just for completeness, you actually plug in some matrices here, which you learn in the learning process, but I won't care about that right now. So basically, this is what we have now. We have the tokens here. We feed them into the RNN, which sort of propagates forward. And we have the attention, which sort of can ask the vectors backwards, right? And this goes on and on. And this attention mechanism turned out to be very powerful in itself. So researchers started asking themselves, well, do we really need the RNN structure at all here? And this is where the mighty transformer starts to take its shape. And the transformer is architecture that almost all the new modern language models actually use. And the way it works is basically we take the same picture, but we remove the RNN completely. So we just use vectors for these words. So H0 now is just one vector for a word vector basically for X0 and so forth. But we still keep the attention here, so we let this, the attention mechanism is the same. So this can sort of ask H0, do you have something that is valuable to me, and so forth. And the second thing is that we add this a nonlinear dense layer to our time step. So just a simple, simple propagation forward here in this network. And introduce this parameter W, which you sort of learn here. And then, of course, this is deep learning. You just add a layer. Why not? And so you take this as your new state. This is just the identity. So this H2 is actually R2 here. And then you do the same trick. You do the attention mechanism. So this can sort of ask around backwards, do you have something for me? And then you feed that through another nonlinearity, and so forth. And finally, you do this for as long as you want, maybe 12 layers. And you have this sort of input tokens downstairs. You propagate upwards, and you sort of get this higher order attention mechanism that sort of can ask around. And in the end, you have this output layer, which is just probabilities over your English words. And there are some more bells and whistles to this that I won't have time to go into here. But this is basically the idea of the transformer model. So when we want to train this on unlabeled data, which is basically what we do when we want to train a language model, we just create input-output pairs of any chunk of text. So we take like 1 gigabyte of Wikipedia data, and we just split it into sentences. And then this is a sentence from Wikipedia, the dog ate my homework, and as output, I just shifted one to the right. And I use this as training data, right? And I do this, and so I get like millions of sentences, sentence pairs in this fashion. And then I try to train the transformer so that if I input the dog ate my homework, it should output the dog ate my homework stop there. And I do this for all the sentences, and I want to optimize some cross-entropy loss, for instance, so that it sort of performs well. All right, so this actually gives me a language model. I take this transformer, I train it on a bunch of unlabeled data, and I will get something that can maybe predict words. So if we want to use this to predict the next word, we do as following. So here we have this sentence, where did I put, and we're going to guess the next word here. So then I just plug in where did I put, and I let things trickle up or percolate through this transformer, and I use the last state here to actually try to predict the Y3. So then I play the same game, list all the words I can think of, and the language model will actually give me the probabilities of these words, right? So for instance, now my seems to be pretty high probability, so let's choose that. And of course you can use this to just build up more longer sentences and let it actually generate text by saying, okay, so now we take my, then we take where did I put my, and then we plug that in here. We do the same trick. We will get another prediction, and we can just keep on going and actually generate text from this model. All right, so that's pretty cool. And what we do here, if you think about it, is we take this chunk of text, where did I put, and we let it go through here, and this vector coming out here, we use that as a representation of the whole block of text that we have here, so the whole sentence. And what we are using this for at Seal is because we're mainly interested in text classification, as I said. So what we do there, so we deal with contracts instead of than Wikipedia. So we take contractual data and we take gigabytes of contracts and we just train this language model on these contracts instead. So this will give us a language model tailored specifically to contractual data, right? And then we get a lawyer, and they will annotate the contract or some contract. So what we're after is we're going through the contract sentence by sentence, say, and we're looking for legal entities within the contract. So for instance, legal entities like force majeure, which basically just says in a contract what party is responsible in the event of a force majeure, like an earthquake or something. So if we wanted to predict that, we just get a lawyer, go through like 100 contracts or something, and just mark up all the sentences that are force majeure related. And we use those contracts, all the sentences from those as input, and we have the labels provided to us by the lawyers, right? And we use this transformer, and this last state was some sort of representation of this whole sentence, and we just add a classifier on top of that representation. So for instance, a logistic regression is something very simple. And the hope is that this big language model contains a lot of information about how to actually classify this thing. So it makes the classification process a lot easier. And one of the motivations for actually using this is the following. So, of course, annotating data is expensive, and you want to annotate as little as possible in order to get good models. So this is 3 graphs. Let's just focus on the first one here. Basically, this is taking the language model classification architecture, and the blue line here is when you don't pre-train it on unsupervised data before. You just use the architecture and train it directly on your classification task. And the x-axis here is the number of annotated examples. So we see here, we start with 100 number of examples, labeled examples. We're at like 40, 50 in accuracy or something like that. But if we do the same thing, this green line here is actually when we have trained the language model first, using a lot of unsupervised data. Then we see that if we use the same number of 100 examples, we really get down to 10% of error rate here, in this case error. And for this unsupervised or untrained network, we would really have to go like asymptotically to 20,000 examples per to get to the same error rate. So this really tells you that in order to minimize the number of examples you have to annotate, it's a good idea to use some pre-training first, right? So in case of lawyers, which are expensive, you might not have to pay them for a long period of time. And of course, that's very useful for us. And here is the same, more of the same, but this is something we did a master student at Seal, where we did the same thing, but other sort of methods of using unlabeled data to pre-train your network. So not in terms of language models here, but others. And let's just focus on the first one here. And the black and red are pre-trained language models, and the other ones are not pre-trained language models, but pre-trained in some other way. And you see the same sort of phenomena occurring here, that accuracy is, you don't need many examples in order to get a good accuracy. All right? So, I have Slack here. I don't see any time really.
Yeah.
Okay. Yeah, so I just wanted to quickly go through a few of the more recent language models because I think they are pretty cool. So I'm not going to spend too much time here, but these are some of my favorites at least. So this first one here is actually a variant of the RNN architecture that we considered at first, and it was the first model that I sort of played around with, which gave really good results. So I was very happy with that. And then last summer, OpenAI released this GPT model. GPT stands for generative pre-training, I believe, which is exactly what we have been describing so far with the transformer. And it gave very good results on a number of tasks. But then came BERT here 6 months ago from Google and sort of just crushed everything in its way. It was a very exciting time. And then finally, a couple of months ago, OpenAI released their second version of this GPT, which they trained on ridiculous amounts of web pages. I think it was like 40 gigs of that, and it was so good that they did not dare to release this. And I just did some math, and it's the code is almost out there, and they have described exactly how to actually train it and what the data they use. So you can sort of just get the data and get your $45,000 approximately, and then you can actually train that for yourself. Oh, sorry. All right, but you see here the trend is really let's just make everything bigger and plug in more data, and that's I guess that's a fun game to play. So let's play. Okay, so an interesting question for me is like, okay, so what do these language models actually learn? And of course, it's very hard to know what goes on in the minds of deep learning models. We know that. But so the easiest way to do this is to just try to probe it in some sense. So you try to use your language model for some tasks and just see, okay, so how do you perform on this task? And that's, well, a good measurement, I guess. But they seem to learn representations that make them suitable for many NLP tasks. And we'll be looking just at a small section of these. So for instance, here we have BERT on glue. So glue here is an ensemble of tasks. So GLUE stands for General Language Understanding Evaluation or something. And it's basically 8 tasks, which has to do with understanding text. And we train BERT on these various tasks and just see how well does it perform. And so the first one here, MNLI, the data set, this data is entailment classification. So basically it means you give BERT 2 sentences, and it tries to predict, is this the continuation of this sentence, or are they contradictory, or are they neutral to each other? I mean, they have nothing in common. And as you see here, so BERT, especially the large BERT model, performed very well with regards to previous models on this. And QP, this task here is semantic equivalence. You ask, are these sentences semantically equivalent? Also, BERT outperforms everything from before. QNOI is question answering. You ask it questions, it tries to answer. SSD2 is sentiment analysis, and so forth. So these are, you just probe it by asking it these NLP type questions and see how well it performs. And it outperformed all the others. So that's pretty cool. Yeah, and also people just are. So Jan Goldberg is a fairly famous NLP scientist, very skeptic against most things, but even he sort of realized that these actually perform fairly well on his problems. So it seems like these language models actually learn a lot of things about language, which without us telling it to learn it, it just learns to predict the next word, basically. That's pretty cool. And I think also the title of this G2 paper from OpenAI, this big language model, the too dangerous to be released language model, is pretty fitting. So it was language models are unsupervised multitask learners. And the idea here is basically when you train a language model on all this text, it sort of implicitly learns a lot of things. It learns to answer questions in some steps. Because that will help it in its task to actually predict next words. So you implicitly, without telling it, it will sort of learn multitasks in the process of doing that. So for instance, you could, for some pretty weird reason, ask a GPT-2 just to translate French into English without having ever trained it on this. So for instance, the way you do it, how do you do this? So the way you do it is like this. So je suis un papillon equals I'm a butterfly. Le chat évolue equals what? And you just let the language model sort of start generating here. And you will get a sentence, or you will get words. And it turned out, I mean, surprisingly enough, it turned out to actually perform quite well in this setting. So it turned out that there were some French language in this data set, of course, but still it was never asked to actually do this task whatsoever. And of course, it was not as good as state-of-the-art neural machine translation models, but it still outperformed some of them. So it's fairly cool what you can do without even telling it to do. All right, so I think I'll have to skip this, but is bigger better? I have maybe an optimistic maybe. I'm not really sure. So these language model papers from Google and OpenAI, they sort of have some graphs depicting the bigger you go, the better you perform. But I think we need more experimentation in that regard. So we'll just leave with the conclusion here. So it seems like by doing this pre-training of language model, you get useful representations of your data. This block of text, and you get this vector in the end, and you can use that in a very good way to do many things. For instance, classifying sentences in the document. And so I will leave you with my recipe for text classification here. So the first thing you do is just you train your language model on labeled data for your domain. That's usually fairly cheap to come by, at least compared to actually annotating data. And then once you have that, you just add a classifier on top and you train on labeled data. And these steps are actually really simple to perform nowadays. There are foundations like Fast AI or schools where they provide like Google Colabs where you can just do this yourself within a day. So I'll leave you with that. So thank you.
Great, thanks, Aron. So I think we'll have time for maybe one question before we need to move into the other hall. So is there any one from the audience?
You're a former employee, so.
So I don't know if this makes sense, but do you think you could mix labeled and unlabeled data together by putting some special token like please classify and then the actual target, and just using the language model on that to predict the labels or to classify?
I'm not really sure I understand what you...
So you have an example which is labeled. Yeah. So this agreement blah blah blah, and then you put a end token and then a limitation of liability, like a label, and put that together with all the other sentences. Yes. And then just let the language model predict the last token.
Yes, I think you can do something to that. I have never tried it, but I mean, a lot of the other work, the way you train on this glue set, for instance, it's sort of reminiscent of your idea, I think. So it's it does not sound far-fetched.
Okay, great. Before we move into the big hall, we'll give Aron a last applause, and thank you very much.